This is Dr. Paul Baldock, and he's going to be talking about why bone is more than just a stick to hold you up. I think you can tell by the title of that this is not your straight up and down kind of scientific presentation. Paul did his PhD at the University of Adelaide and came to Garvan in 1998 and has been here ever since. Must like it here.
Love it here.
Yep, he's head of Skeletal Metabolism Laboratory, where he examines the signals that bone uses to regulate other tissues and how bone medicines can affect other organs. So please welcome Dr. Paul Baldock.
Thank you. And first, before I say anything about my work, the most important thing I have to say beyond all of my research is thank you. Right? From a guy who's been here a long time and knows how important any donation is. What we do is sadly very expensive at times. Work like this I'll show you today, the government has not funded. They have refused to fund it because it's too big a step. Right? Government funding is by its nature, and perhaps should be, quite conservative. They're like insurance companies. They want to put money into things that they know will give us an advance. But if that advance is a big step, they get cold feet. And so, ironically, perhaps the more important, no Nobel Prize winner in Australia has ever gained government funding for their research. None of them. All right? The more reckless the work is, the less you're going to get money. But those big steps are the ones we want to take, and it is money from people like yourselves that give us the opportunity to make the big steps, because the government will fund the little steps, but we want the big steps. So sincerely, thank you. Every little bit helps, and I'll show you today what I think might be a big step. So here's what we're used to thinking the skeleton does. It holds us up, it walks us around, it provides us with calcium, and generally the talks you hear about bone are when bone's doing something wrong. Osteoporosis, bone cancer, it's always a problem, it's always a problem. My work, I try to be positive. I look at what bone does that's good. I'm quite unusual in that. And what I want to show you today in particular is not the regular stuff bone does, but some different stuff. And in particular, glucose homeostasis, diabetes, all right? Our control of our blood sugar. Becoming an increasing problem that I'm sure you're aware of, our inability to convert the glucose from our food into our cells. And diabetes is an increasing, type 2 diabetes is an increasing problem. And what I want to show you today is the role that this guy has in that. And I think a potentially amazing role. So first, can't get around talking about a bit of bone. I'm a bone guy, all right? I am a bone researcher, trust me. And essentially bone, in terms of its cellular structure, is extremely simple. There are 3 cells. It's a very basic thing. The osteoclast, clast means break down, so bone breakdown. These cells eat your bone. Osteoblast, blast means make. These guys make your bone. And essentially, that's it. You will replace your skeleton about every 10 to 12 years, as it's a stress member. It gets micro damage and that is replaced. You turn it over, you create it, you grow it, and you maintain it extremely efficiently throughout most of your life. As you know, when we get older, that maintenance breaks down a little bit. Osteoporosis, particularly as we get over the age of 55 or 60, becomes increasingly important. But I'm not going to talk about that. Yeah, I'm sure you've heard enough about that. I want to talk about something different. So 3 cells. There's another type of cell, the osteocyte, which is these guys that get buried. They're throughout the bone, and you can see in this is a section through bone. Here's a big osteoclast. It's in a pit that is eating out. They secrete acid and they digest the bone. The osteoblasts come along and fix it up, and it's just those take off, put on, and that's the balance you've got. And then these guys, the osteocytes that are buried in bone, essentially they tell everyone what to do. All right? And quite recently, certainly 10 years ago, this conversation wouldn't have been happening. But we're learning very rapidly, and at the Garvan we are world leaders in this, that bone does more than just, these cells do more than just modify and maintain your skeletons. They do other things. We know that the communication, we've always known the communication is very complex. Here's a little diagram. There's your osteoblast, there's your osteoclast, and that's just a fraction of the conversations that go on between these cells to make sure that your skeleton is kept intact. We've always known that bone has a great deal of regulatory input. There's lots and lots and lots of systems telling bone what to do, particularly because bone is your calcium store. And without calcium, all hell breaks loose. Your nerves need it, your muscles need it, everything needs it. Essentially, it's the ocean, right? When we came out of the ocean, we took the ocean with us. Nothing has managed to breed without the ocean. You need an egg, you need a womb, you need to take the ocean with you, and that's what the skeleton is. And so it is a bank of all of those salts that we used to have in the ocean, and we take it with us. And without that, we do not work, and we do not work at all. So we know that lots of other systems, like your kidneys or like your guts in particular, are telling bone what to do, helping it put the calcium in, helping it take the calcium out, right? What we're now, and what my work focus on, is bone talks back. It's always been an organ that just did what it was told. And it got told by lots of things, and it does a very careful juggling job. But what I look at is signals that come from the bone and tell other things what to do. Bone gets a chance. And I'll just give you a little example of a paper, a piece of research that came out not long ago that gives you an idea of how strong these effects might be. This is a cross-section of human bone. See these little dots? They're those cells, those osteocytes that are embedded in the bone, the ones that tell everything what to do. And they're amazing cells. They look like nerves. There's his little cell body, and look at all his little processes. See all those little fingers coming out? They talk with all the other osteocytes embedded in the bone and with the surface. That's the surface of the bone there. You can see how many go up there. They are coordinating essentially how your bones respond to load, essentially how they do everything. All right? And this research paper knocked these things out. It just shut down their ability to work for a couple of weeks. And this is what happened, right? Every single bit of fat and it was a mouse in the mouse's body disappeared in 2 weeks, right? There was none left. That's a normal mouse, and that's his tummy. You can see that's that visceral fat that Charlemagne was talking about. It's gone. This might be a bit hard to see. We'll go down to this one. This is a testicle, and this is the peritesticular fat pad. It is just a fat pad. Look how massive it is in the wild type. And this is the mouse that has those bone cells disrupted, right? It disappeared. And so what it tells us is that there are signals coming from bone to other organs, and particularly in this case to fat cells. And not only are they coming from, they're massive and they're extremely rapid, because in 2 weeks it was all gone. And believe me, there are huge processes that do not want you to lose fat, and I'm sure we all appreciate that. So it gives us an idea that there are big signals not only going to bone, but coming away from bone, right? And if there's a message from my talk today, is that the organs are talking to one another. And what I'm trying to do is find out what those conversations are and see if we can nick them and use them for our own evil advantages, all right? And I think we've found one today. So the other thing, this is a little mouse. This guy's been on a high-fat diet and this guy hasn't. Right, this is its femur, its long bone, so its kneecap would be down here, and this is going up to the hip here, and you can see the bones, the end of our long bones are full of a fine mesh of bone covered in a very thick outer layer, okay? And this guy weighs much more than he does, so his bones should be big, right? The heavier you are, the bigger your bones should be. It's one of the standard rules, big boned. However, it's quite the opposite. You can see how much bone that the high-fat fed guy's lost. Not only this thin cancellous bone, but the critically mechanically important cortical bone. All right, so not only is bone regulating fat, but fat's regulating bone. So there are cross conversations between the organs. In terms of how we thought everything worked, it was always the brain down. There's a small gland called the pituitary. It hangs off the bottom of your brain, and it regulates almost every hormone you've ever heard of. Estrogen, testosterone, thyroid, growth hormone, IGF-1, all of them. They're all regulated, and we always thought it was top down and the organs did what the brain says because it was a central coordinator. And now what we're finding, and I'll show you today, is that there are conversations going between, and very powerful conversations going between. And so what if there's a take-home message, it is that there is a whole new level of conversation going on between the organs, without the brain, and what we're trying to do here is find out what they are and can we use them to try and modify what we want. Because clearly if we found the one from the osteocytes in the first place, reducing fat mass wouldn't be a bad thing to do. And so what I'm going to show you today is something that we think might regulate diabetes. Okay, so a little bit of data. This is a graph from a mouse model we made, right? It is a mouse that has had a gene, as Shalimar talked about. A gene has been taken out of this mouse, right? It's not quite that important what it is. It's a receptor for a signal that regulates how much you eat, all right? But we've taken it out just from the osteoblast. So the rest of the mouse is completely and utterly normal. Nothing's changed at all, but in the cells that make bone, we've made one little change. And we made that change because we thought it'd increase the amount of bone, and here's a little picture, and it does. And that's exciting, all right? So we can increase the amount of bone, and if you have osteoporosis, that's important. But what I want to talk about today is, what's that got to do with diabetes, right? The quick answer and the answer 10 years ago, absolutely nothing. And frankly, in this example, the answer a year ago would be absolutely nothing. But what we found is a huge change in its regulation of glucose. And why is that important? Diabetes. All right, has anyone here heard of diabetes? Exactly. And the reason you've all heard about it is because it's coming heavy. All right, diabetes is a global problem. This is a graph. And just to give you an example, those colours there, that's 1 in 5. Right? The next colour down, that's 1 in 6, 1 in 7. The next colour down, 1 in 8. All right? Us, we're at about 6 or 7%. And this is 10 years from now. All right? 1 in 5, 1 in 6, 1 in 8. Billions, millions and millions of people. All right? It is coming, and it is coming hard. And frankly, the only thing we've really got is insulin to put back in, and it is not that good, right? We need something better. And of course, I wouldn't be talking about it unless I thought I had it. So what is diabetes? It's really very simple, right? Diabetes is a problem with the function of a hormone called insulin, okay? And essentially, insulin puts food into our cells. That's all it does. A spectacularly important thing to do. So when we eat, the food that we eat gets converted into glucose, sugar, all right? Our cells burn sugar. We're essentially small combustion heaters. That's all we are. We take sugar and we burn it, and we take the energy that's released from burning that sugar, and that's how we run, right? We're good old-fashioned combustion heaters. None of this fancy fangled stuff. We are very simple wood-burning engines, but we need glucose to do that. In fact, we can burn some other things. Our brain can only eat glucose. It can eat nothing else. So our ability to control glucose is fundamental to our health. And the thing that does that is insulin. So normally you eat a meal, the amount of glucose in your blood goes up. That is sensed by an organ called the pancreas, a sneaky little organ. Don't trust it. It'll give you cancer and leap up and get you. But what certain cells in the pancreas do, they make insulin, all right? Insulin links to the cells and says, let the glucose in. So insulin is the gatekeeper, okay? The better your insulin works, the better your glucose goes in, the more your food gets converted into your cells, and the more you can burn, all right? Problem is too much food, too much glucose, and it gets stored as fat, as it should, because back, a century, 2 centuries, 1,000, 1,000,000 years ago, food was hard to get. So if you've got excess, it's a bonus, and you store it in fat because you'll need it later. The bear needs to get fat to be able to make it through winter. The gazelle needs to get fat to make it through summer. So our systems are designed to store whatever excess we get. Unfortunately, now we always get excess. And that is one of the true drivers. Obesity is one of the true drivers of type 2 diabetes, and I'll show you what happens. So when we get a continuous influx of glucose, right, it disrupts the ability of the insulin to signal. And so we come down here to type 2 diabetes. The signaling process gets worse and worse and worse. The glucose doesn't stop coming because we keep eating, and so the pancreas has to make more and more and more insulin because we are slowly going deaf to the insulin. And eventually, the pancreas has had enough, it gets exhausted, and its ability to make insulin fails, and that's true diabetes, and that's when you need to put it back in yourself. And it is not a great alternative. It'll work, but it's far from perfect. All right, so what we actually truly need is to change this, right? Can we fix up us going deaf to the insulin, right? Can we make us more insulin sensitive? Can we make the insulin we've got work better so the pancreas doesn't get exhausted and keel over? So these mice, back to the mice. Remember, we changed one gene in the bone, in the cells that make bone, nothing else. Didn't touch the pancreas at all. And we found that, so islets. Islets are the cells that make insulin, so you want lots of them. We found that we had less of them and the area of those was smaller. This, can you see that that's a blue outline there? Right, the dark brown dots are the cells that make insulin, right? They're the ones that will die in type 2 diabetes because they get exhausted. They're the ones that we want to help. And we saw in these mice that they had much, much less of them. And their insulin was much, much lower. And we were worried we'd broken them, right? So we had a look at how they respond to glucose. It's very easy to test how good your insulin system is, and it's to have a meal and track how fast the glucose goes away. Because that's what insulin does, right? And we can do that in mice. It's very simple. Give them a little lolly. They love it. You know, they eat boring chow food all the time. We give them a little sweet and they stand up and gobble it down, waggle their little tails. So you get a meal. The meal goes in, it gets digested, and then you get a flood of glucose into the blood. All right? That triggers the insulin, and the insulin puts it into your cells. There is no point having very sweet blood. It does you no good. In fact, it does you harm. So we want the glucose out of the blood and into the cells where A does no harm and B does you good. And we can track that. So here's our little mouse where we've changed the bone gene, and you can see he has a little meal here, and he puts his glucose away with much less insulin. And we just thought we'd broken him. So we made another one where that system, this is an enhancement of that system and that's a deletion, and he's absolutely the opposite. He needs a whole lot more. All right? We weren't quite sure what was happening. So we took these bone cells, and we can grow them in culture in a dish, isolated from the rest of the animal. They're just there by themselves. All right? We feed them and they're perfectly happy and off they grow. And then we take the fluid that they grew in, which contains everything that they secrete. Right? So it's an idea of what signals that they're putting out. Right? So we take that fluid and we put it over onto the cells that produce insulin. We put them onto these guys, also in culture. All right? So there is no rest of the body. It is direct from the bone to those cells to see if there was a signal. And we saw a spectacular change. Two things to notice. This is a normal, and then when these are the insulin producing cells, when you give them the fluid from bone cells, the insulin goes up. Right? So one that says bone is talking to these cells, which is an amazing thing. Those sorts of conversations, and they're direct because we took it from the cells to the cells. There's nothing in the middle. Right? So bone is talking to these cells and talking very strongly. Bone wants sugar. You can see, wants that sugar in. And as I said, you turn your whole skeleton over every decade. It's very busy, and it needs energy to do that, and that's what glucose is. But when we did the same thing from these mice, that signal is blocked, significantly blocked, right? And so A, bone talks to insulin, and B, we have some sort of control over that signal. But is that good or is that bad? Essentially, have we broken it or have we made it even more sensitive? So they're the two things. Is it good? Is that insulin less because it's simply not needed? Or is it bad? Is it needed and we've just broken the system, right? And that's the critical question. And we can test that, and we did that. And this is a couple of weeks, right? This is brand new. You're one of the first people on the planet to even hear this. So we looked well. We took all of that fluid that was coming off of those bone cells, and we compared the blue to the red, right? We compared what proteins were in there using a system called mass spec. It gives you a list of every single protein in that mix and what the levels are. And we looked at what ones were different. And we had a look at one. This is one of the ones we prioritized, osteoglycin, which is the perfect name because it means bone sugar, right? I swear I didn't make that name, right? And what we found, that it is exactly what we want. It's not bad, it is good. So those mice that had the very small number of insulin producing cells, they simply haven't needed any more because their system is so powerful at doing what it does. And I'll show you this now. So what we've done is we've given mice osteoglycin. So way back here, we've given them 4 hours before, we've waited, and then we've given them the little meal, right, to see how they deal with their glucose. Okay? And so the little white one's a normal animal. Then there's the grey one and the black one are increasing doses of this protein osteoglycin. Okay? So here's the little meal at 0, and you can see the blood sugar goes up as they digest their food, and then it comes down as it should as the insulin. So this is insulin doing its job. All right? Insulin is taking the blood, the glucose from your food that went into your blood and putting it into your cells. That's what you want. Remember, your cells can burn almost nothing else but glucose, so that is critical. And the thing on this graph is how much insulin they needed to do that. So you can see that they're reasonably similar, these guys. It's a bit better, but they're reasonably similar. But this is the amount of insulin they require to do that job. So here's the white one. You got a big rise in insulin and it comes down as the glucose goes away. And here's the highest dose. They barely needed to make any insulin at all to do it. All right, so what this means is that this animal here, completely normal but for a previous dose of this protein, is able to put its glucose away almost without using insulin. All right, and so if we remember back to type 2 diabetes, the problem is that we go deaf to the insulin, right? So what we need is something that makes our insulin work better. And in this case, you can see the magnitude of the change. See that little gap? Compare that little gap there to that gap there, right? 5, maybe 10 times more effective just with this one protein, and a protein we found from bone. It's insane, right? So what it suggests is that these conversations between, and remember it's direct, between the cells of bone and the cells of the pancreas, because we did it in vitro. There's no other thing. We took it from one cell and dropped it on another. It is a direct conversation. And so 10 years ago, 15 years ago, we'd only think of the pituitary in the brain. And so these signals between the organs are there, and we can find them, and they appear to be extremely strong. And if bone can control your diabetes, what else can it do? And if bone can do it, then what else can do it? So there's a whole new system that is out there for us to try and discover to get our greedy little hands on and use. All right, so could someone who has type 2 diabetes or developing type 2 diabetes use this signal made by osteoglycin to make their insulin work better? Because the important thing would be if their insulin works better, it gives their pancreas a break, and then those beta cells don't die. And if they don't die, then you don't need to start taking insulin, because that's a problem. All right, so this, in its way, is a potential cure for type 2 diabetes, and found from this brand new conversation that we're slowly starting to understand. And so just a little bit of, to give you an idea. So that mouse we made with the gene missing from the bone, we made 2 of those, right? We made one where we took it out very early in those osteoblastic cells, and one we took it out late. And we saw the one we took it out late, the bone thing happened, but the pancreatic thing, the glucose thing, didn't happen at all. They were absolutely normal. All right? And the one that we took out early did. And when we look at the levels, this is osteoglycin that cells produce. It makes a lot when they're really young. Don't we know that story? And as they get older, they make far less. All right, so it looks like there is a specific window during these osteoblasts' lifespan that they are making this and controlling it. And it makes perfect sense when they're early, when they're just about to get ready to do the hard work of making bone, they're making sure that there's plenty of energy around, plenty of glucose, plenty of insulin signaling to enable them to do it. Right? It's like them having a big meal before they go into action. So it fits in with the biology of the whole system. And so that's nearly me. So just to summarise, and the statement I wouldn't have dared make, 5 years ago, 10 years ago at all. Bone-forming cells play an important role in controlling our glucose and insulin economy. Right? Who would have thought it? Specific proteins made by those bone-forming cells have, believe me, powerful effects to increase insulin sensitivity, and that's what we want. We don't need more insulin, we need our insulin to work better. Because people with type 2 diabetes, their insulin's really high because it's there trying to work. So if we can just give insulin that little leg up to get the glucose in, then the whole problem gets much more simple. And so one of these, and who knows how many more there are, osteoglycin has a remarkable ability to increase insulin action, right? Potentially, as I said, reversing diabetic changes. And so my take-home message from this whole thing is that there are powerful regulatory signals passing between bone and other organs. And it won't be just bone, it'll be the whole bunch. All right? What we're finding is that there's a far more fundamentally interconnected biology than we ever thought existed. And our ability to change genes in a specific cell lets us see that. So we changed it in the bone and we had a look around and we saw a change in the pancreas. We wouldn't have done that if we hadn't even thought that was going on. And just to have it said, the Garvin is a perfect place for that, right? I interact with the neuroscience program, the diabetes program. We all work together. And this sort of work suggests we need to work together more and more and more. You sit there in your one organ and just play around, you're going to miss it. So the ability for us to collaborate together, and we do, and it's been a cornerstone of my career, we need to work together to find these unique conversations that we can use. So as I said, far more integrated than we imagine, and inter-organ endocrine signaling. As I said, it was always our brain, always the pituitary doing everything. It's not. There's a whole new level. And the last thing I would leave us with is the idea of syndromic drugs. We always take one drug to do one thing, and then we worry about the side effects. It does this, it does that. You think about how integrated it is, of course they do. The idea that you have one drug to do one thing, it's not going to happen, right? But rather than that be a problem, it has the potential to be an advantage. So if you have a drug, let's say, that works a little bit on bone, and a little bit on fat, a little bit on muscle, and a little bit on the pancreas, to all mutually support themselves, rather than having negative side effects, you can have positive side effects. So ideas metabolic syndrome, the whole thing gets trouble. So can we find conversations that touch on all of those things with a single protein to work for us? And you would need a much less powerful drug, and it would have multiple advantages rather than multiple problems. And so rather than trying to have one drug for one organ, can we have one drug for a syndrome and use it to work on all of the aspects of the disease to make it a little bit better? And I think, for me, I don't see any other way forward than that. And I will thank you for your time.